Now we want to talk about propagator matrices briefly. Let's consider the typical equation, the typical system, and I'm not going to read it to you. Here's our typical system. Now, this system presumably has a solution, or a psi matrix characteristic solution. We're going to define the matrix phi a function of t and s. Now we really regard t as the variable in this equation, and s is just a variable that stands for some parameter. It's just really a parameter of the solution, and we'll see how that works in a minute. Phi of ts, though, is going to be defined to be psi of t times psi inverse of s. Now, this matrix, phi of ts, defined this way, in the first place, and I've kind of got these out of order, but I've got the statement, this is equal to the identity if t equals s. And this should be obvious if you think about it a little bit. If t equals s, then you've got phi of s, phi inverse of s, and a matrix times its inverse is the identity. So that's kind of a no-brainer. Assuming that psi is a fundamental matrix, and let's write that in, so we're sure that we understand that that is a condition of what we're talking about. If phi of t is a fundamental matrix, then this matrix is a solution of the equation. In other words, phi prime equals p of t times phi. Now, how do we know that? We know that because psi of t being fundamental is invertible. Psi inverse of s is therefore the inverse of psi of s. And since this is an invertible matrix, multiplying it on the right, multiplying psi of t on the right by this matrix still gives us a fundamental matrix by previous theorems. Anytime we multiply a fundamental matrix by an invertible matrix, we get another fundamental matrix. Now, there are transitivity properties and other properties. Your book will talk about those, but if you understand that this is the definition, it's not difficult to understand and prove those properties. The main property that I'm going to simply assert at this point without proving in detail is that if y of t is a solution, then multiplying that solution at some time s by the psi of ts matrix defined here gives us our y of t. And in that sense, this matrix propagates a solution from time s to time t. In particular, one of the useful properties of this matrix is simply, and the one we'll illustrate with an example, that if you have an initial condition, y of t naught, if you multiply that by the matrix phi of t, t naught, you're going to get the solution y of t. So that phi of t, t naught times the y naught that we specified for our initial condition here at time t naught is going to give us our y of t function. So let's see how that works out. And in just a simple example, I've had the foresight this time to generate a lot of matrices that have integer values of the integer eigenvalues. So I chose one of them here. So we're going to take this equation y prime of t equals 2, 3, negative 1, 6 times y of t, and the condition y of 0 equals 1, 1.